Okay, in this video, we're going to talk about examples for lesson 7, where we used Venn diagrams as the primary mechanism for solving and also subsets. And we'll try to tie that together with some formulas as well as we go through just a short number of problems. First one says, a community college has 1,000 freshmen, 800 sophomores, 700 seniors, and 500 juniors. If a student is selected at random from this college, what's the probability that the student is a junior or a senior? So pause the video, give this one a try, and see what you got. Okay, so in terms of the OR formula here, this we're talking about selecting a student at random, and we want the probability that the student is a junior or a senior. So this is an OR case compound event probability, and that means we're talking about the probability that we have a junior, or I'm going to use the union symbol, or a senior. All right, which from formulas we know is the probability of junior plus, because OR is add, plus the probability of being a senior, but we would have to subtract off the probability that the person is a junior and a senior at the same time. Right? The thing is, though, a student cannot be both a junior and a senior at the same time. So that means that this would definitely be 0. And so all we have to do is find the probability of being a junior and probability of being a senior. Right? Now, this video is mainly about talking about Venn diagrams. So let's show the Venn diagram situation for that. If we have all the students in the school, right, all the students fall into one of 4 categories. So instead of using circles, I'm just going to divide this universal space of all the students into 4 quadrants, one for freshmen, one for sophomores, one for juniors, and one for seniors. Right? And then I'll just put the numbers here. So there were 1,000 freshmen, there were 800 sophomores, there were 700 juniors, and then there were 500 seniors, right? And so these spaces here of being a junior and being a senior, those two things are what we call disjoint events, right? You can't be a junior and a senior at the same time, right? And so that means we're going to add this up. So if I was using the Venn diagram, I would just say the probability of being a junior or a senior is going to be the total number of students. So I would add all the students up, right? This is 1,000, and let's add them up real quick, 1,000, and then 800, and 700, and 500. All right, and so we end up getting that there are 3,000 students total there, 3,000 students on the bottom because we're selecting one student out of all of them. And then we would just want the ones that are in the juniors or the seniors, so we'll just add up the 700 and the 500, right? And so that turns out to be 1,200 out of the 3,000 students, and that turns out to be 40%, right? So it would also match what we did if we used the OR formula. The probability of being a junior, since that's a simple probability, would be out of all 3,000 students being a junior, which is 700 of them. And then the probability of us being a senior, again, a simple probability out of all 3,000 students, what's the probability of being a senior? 500. And then we would add that. And then since we have common denominator already, they add up to 1,200 out of 3,000, which is that same 0.4. Okay? So the idea here is you could use a Venn diagram in many cases when you could also use the OR formula. Okay? All right, let's take a look at another problem. So this one says we have 2 events, E and F. They're sort of generic events. We know the probability of event E is 20%, the probability of event F is 50%, and we're told that E is a subset of F. And then it says to draw a Venn diagram to find the probability of E and F, probability of E or F, the conditional probability of F given E, and then E given F, and then answer the questions, are these independent and are these disjoint? So go ahead and try pausing the video and try this problem out. Okay, so we'll start by drawing a Venn diagram representing this. So let's see, we have the universal set, and it says that E is a subset, which means E is completely contained inside of F. So if I were to draw this, I would maybe make a big circle for F, and inside that I'd have a circle for E. So E is completely contained inside of F. That's called a subset. Okay, and then we're going to label the probabilities. So remember we said that whenever we work with Venn diagrams, we should try to label the innermost probabilities first, right? So, well, let's see, the innermost probability here is E. The probability of E is 0.2, so inside the circle, I'm going to use probabilities here. You can label Venn diagrams with either counts or with probabilities, you just have to be consistent. So I'll put 0.2 there. And then the probability of F is 0.5, that means everything inside the F circle has to be 0.5, but we've already accounted for 0.2. That means 0.3 is left over right there, so that adds up to a total of 0.5. And if that represents 50%, then everything outside of F has to represent the other 50%. So that would be 0.5 there. So that's a completely labeled Venn diagram. Okay, let's go ahead and use it to solve these probabilities. So the first probability is to find the probability of so A, is to find the probability of E and F, right? That and means the intersection. That means you have to be inside the E circle and also inside the F circle. Well, the entire E circle is inside the F circle, so really that would just be everything inside the E circle. And so just by inspection from that, it would be equal to the probability in the E circle, right? 0.2. Okay, the second part, B, says to find the probability of E or F, and that means the union. So that means you can be included in this if you're in the E circle or if you're in the F circle or both. And so if I include the E circle, I get the 20%. If I add the rest of the F circle, I get 30 more percent. So that's going to be the total of everything inside E or F. So we'll add up those and get that that's 0.5. So 50% chance of E or F occurring. Okay, and then the conditional probabilities. So the first one here, let's see, D says to find the conditional probability, the probability of F given that E happened. Okay, so I'm going to use the idea that the denominator of the fraction is determined by the condition. So the condition is E, and that means I'm going to put some either counts or probabilities that represent all the ways to be in E. So E would be the 20% that's in that circle, inside the E circle. So that would be 0.2. In other words, I'm saying inside this circle here, there's a 20% chance of meeting the condition. Now, on the F, for F, I'm going to say, okay, now I want to stay within the condition E, but the probability of that's also in F. And actually, that turns out to be all of that same circle, because all of the E is in F, so that would be 0.2. And 0.2 divided by 0.2 is 1, which means, given that E happens, it's absolutely certain that F has also happened, which makes sense because E is entirely in F. Okay, so that would be that conditional probability. If I wanted to find the other conditional probability in part E, it says find the probability of E given that F has happened. So we'll use the same approach, right? We'll use the F to determine the bottom of the fraction, and that means this time we're talking about the F circle, the entire F circle over here, right? So that's going to be 0.2 plus 0.3. There's a 50% chance of being in F. And then the top of the fraction, the numerator, will be set by how much of F is also in E, has to be in E, and that would be only this 0.2 part. So it'll be 0.2 out of the 0.2 plus 0.5, or 0.3. So 0.3 out of 0.5, and therefore that's 40%, which is saying if you're in the F circle, there's a 40% chance of being in the E circle. If F has occurred, there's a 40% chance that you're more specifically inside the E circle. Okay, and then the next questions are asking about dependence and independence. So let's take a look at those separately. Let's see, for F, to determine whether something is dependent or independent, we want to determine whether the probability of one of the events is going to change depending on the probability of the other events. So for example, I could say, what's the probability of F? And then I could ask, what's the probability of F given that E happens? And we'll question, are those two things equal? Because if those two things are equal, it means the probability of F is just the same, regardless of whether E happened or not, which means it's independent of E. Okay, so they told us in the problem that the probability of F is 0.5, and we just found out that the probability of F given E, that was in part D, let me just work it again. The bottom of the fraction is E, right? And the top of the fraction is the part of E that's in F, so that's 1, right? So the question is 0.5 equal to 1? No, that's not equal, which means the probability of F is changing depending on whether E happened or not. Right? So we have to say that E and F are not and, sorry, E and F are not independent of each other. The probability of E is depending on the probability of F. And we could also have chosen to not investigate probability of F. We could have picked probability of E. Right? This is another way to do the problem. You could say the probability of E. Let's check to see if that's equal to the probability of E given that the probability of F has occurred. Okay, so the probability of E is 0.2. That was given in the problem. And the probability of E given F is out of the 0.5 in F, the probability of E is 0.2, so that turns out to be 0.4, right, 0.4. And so we can see again, those are not equal, so that argues for this being not independent. Right, so I think one of those two ways is the way you should do the problem. You should pick one of the events, find out the overall probability of that, and then find the probability given that the other event has occurred, and if they're not the same, then they're not independent. There is another way to do this, and that is some books do this. They say, okay, the AND formula, right, is this. Probability of E and F occurring is really the probability of E occurring times the probability of F occurring given that E has happened, right? The second probability here has to be a conditional probability, right? But they say if we know that E and F are independent, then we know that the probability of F given E is just equal to the probability of F period, because the probability of F isn't changing. So we end up getting a simpler version of the formula. We can say the probability of E and F is just equal to the probability of E times the probability of F, right? Without having to specify a conditional probability. And so some books call this formula the test for independence, because if that's true, it means that E and F had to have been independent. So if we wanted to do it that way, we could do it that way. That would mean we would find the probability of E and F, right? And the probability of E and F occurring, right, we said was, we did that before, it was 0.2. That was in part B, right? And then the probability of E is 0.2, right? And the probability of F is 0.5. And so we would multiply those two things. I didn't do it this way before, so let me do that real quick. If I were to multiply 0.2 times 0.5, I would get 0.1. Okay, so 0.1. Right? And since those are not equal, that's another indication that these are not independent. Okay? So many books put that in as the independence test, but I actually think that's more of a consequence of independence. It's not really why it's independent. So I prefer this method where you pick one of the events like F, and you check the probability of F and the probability of F given E to see whether or not the probability of F is changing. Okay, let's move on. So the third problem says, of the cars brought into a local auto repair shop require an oil change 60% of the time and a tire rotation 10% of the time, and both an oil change and a tire rotation 2% of the time. What's the probability that a car requires either an oil change or a tire rotation? What's the probability the car requires an oil change but not a tire rotation? What's the probability that a car requires neither an oil change nor a tire rotation, but some other kind of repair? Okay, so pause the video, give this a try, and then see what we come up with. Okay, so we're going to use the Venn diagram approach again. So if I made a Venn diagram for this situation, there are two kinds of repair that we're talking about. We're talking about oil change, right? And we're also talking about tire repair. So I'm just going to abbreviate those, oil and tire. And presumably outside those are other types of repairs other than oil changes and tire. Okay, so let's go back and fill this in. Whenever we use a Venn diagram, we should always fill in from the inside out, right? So it says that we require an oil change and a tire repair 2%. So and here, that's the intersection. So that means we have 2% in here. I'm going to use 0.02 to represent that as a percentage, as a probability. Okay, and then it says we require an oil change 60% of the time. So that means this oil circle has to have a total of 60% in it, but we know that 2% has already been accounted for, so that leaves only 58% to be there. And then we know there's a tire rotation 10% of the time. If I subtract the 2% here, there's 8% left there. And if I add this all up, there's 58, 2 more, and then 8 more. That's what, 68%, which leaves 32% left over, which would be outside. That's the complete Venn diagram. So always start Venn diagram by filling in from the most inside roll out. Okay, so we'll work on each of these. A says, what's the probability that a car requires either an oil change or a tire rotation? So oil or tires. Okay, so that's the union of the two circles, the oil circle and the tire. So just using the Venn diagram, I'm going to add, because we're doing or, so I'm adding. I'm going to add any number that's anywhere inside either the oil or tire bubbles, including the overlap. So this would just be 0.58 or, so plus 0.02 or 0.08. And if you add that all up, that turns out to be 68%. So there's a 68% chance you need oil or tires or both. Okay. The second part, that one says, what's the probability that a car requires an oil change but not a tire rotation? So we have to have oil and we have to specifically not be in the tire bubble. So what that means is I have to be in the oil bubble but outside of the tire bubble, right? So inside the oil bubble here, but not inside the tire bubble. And that's going to be just this part here, the 0.58. So just from inspection on the Venn diagram, that would be 58%. Included inside the oil circle, but not the part that's included in the tires. Okay? And then the last one here says we want the probability that we require neither an oil change nor a tire rotation. So we could write it this way: not oil and also not tires. And that means we have to be outside the oil bubble and we have to be outside the tire bubble. And so that specifically is just this part right down here, the 32%. So we've already computed that when we filled in our Venn diagram. Okay, so those are the three probabilities. Okay, let's move on to the next one. So the next one says, suppose you draw a card from a well-shuffled deck of 52 cards. What's the probability of drawing a 6 or a queen? And what's the probability of drawing a red card or a face card? So pause the video, give it a try, and then unpause. Okay, so as I look at this, we're asking questions like 6 or queen, red or face card, but this is about drawing a card, right? So it actually is a single event. It's not like a compound event. It's a single event. Well, I guess you can consider a compound event, but it's actually just the drawing of a single card. So don't get confused and think it's two cards. It's a card from that. Okay, so for part A, right, we're talking about the probability of a single card being a 6 or a queen. So if I wanted to kind of use a Venn diagram for that, right, there are 52 cards in the deck. I'm going to put a 52 up in the corner to indicate 52 cards there. I'm going to use counts here instead of probabilities, right? I could have a bubble for the 6s, and I could have a bubble for the queens. Well, since a card cannot be a 6 and a queen at the same time, those are two different kinds of cards, then these bubbles can't overlap each other. They have to be disjoint. They can't intersect in any way, okay? And then if I went back and asked, well, how many of the 52 cards are 6s, right? There are 4 suits. There's hearts, diamonds, clubs, and spades, and so there's 4 6s, and there's also 4 queens, right? So the probability that I have a 6 or a queen, I'll use that symbol this time, right, would be out of the 52 cards, right, translates into an add. I would add up all the ways to be in the 6 bubble and also including, or you could also be in the queen bubble. So 4 plus 4, which would be 8. So this would in fact be 8 over 52, or 0.1538. Okay? Okay, the second part asked, what's the probability of drawing, again from a card, a red card or a face card? So if I look at that, let me look at how we do the Venn diagram for that, right? We have to have bubbles for red and for face card, right? But actually the red cards, right, half the cards are red, right, hearts and diamonds, and half the cards are black, spades and clubs. So I think what I'm going to do is, instead of putting a circle for say red, I'm going to divide the entire 52 card deck into halves. So this is called partitioning the sample space, right, into two specific cases, right? I have some of the cards are red and some of the cards are black, okay? Now within that, there are some face cards that are red and some face cards that are black. So I'm going to put a circle like this to represent the face cards. And the face cards are the ones that have human faces, jacks, queens, and kings, just that, okay? All right, so let's fill in what we have here, right? We have, there are how many black face cards? Well, there's jack, queens, and kings, and then the suits are clubs and clubs and spades. Those are black suits, and then there are hearts, and there are diamonds. Those are red suits, right? So if there's a jack, queen, and king for each of these, that means there's 3 of these clubs are face cards and 3 of the spades are face cards. So 6 of the black cards are face cards. So we could put a 6 in that spot in the Venn diagram, right? And the same thing for the hearts. We have a jack, queen, and king of hearts and a jack, queen, and king of diamonds. So there'd be 6 red face cards, right? And that means out of the 12, right, we've to subtract out of the 52, we've used up 12 of them, right? That leaves 40 left, half of those being black, so that would be 20, and half of those being red, that'd be the other 20. So this would be kind of one way to represent with a Venn diagram the situation here. Okay, so let's figure out what we're looking for. We want the probability that the card is red or is a face card. Okay, so probability of red or face card. So it's a simple probability, not a conditional, so that means we're talking about a single card draw out of the 52, so we have 52 on the bottom, but we have to include any way that you can be red, and then we also have to include any way that you can be a face card. We just want to make sure and not count anything twice. So the red cards, right, would be the 20 and the 6, and the face cards would be the 6 and the 6, but I've already counted this 6, so I'm not going to add it in again. But I will include the other 6 to get the other non-red face cards, right? So that means on the top, we have 20 plus 6 plus 6, right? That turns out to be 32 out of the 52 cards, right, which is 0.6154. So if I draw a single card at random from a deck of 52 cards, there's about a 61%, 62% chance of getting either a red card or a face card. Okay, well, let's work on the last problem. The last problem also good for Venn diagrams. It says last month 186 cars were sold at a large dealership. 124 cars had leather seats, 118 had onboard GPS, and 99 had Wi-Fi for passengers. 72 cars had leather and Wi-Fi but not GPS. 70 cars had leather and GPS but not Wi-Fi. 75 cars had GPS and Wi-Fi but not leather. And then 60 cars had all 3 of the options. Find the probability that if I select one car at random from this group, that it has Wi-Fi, or that it has Wi-Fi but not leather or GPS, or that it has none of those options. Okay, so pause the video, give this a try, and then unpause. All right, so this is definitely a Venn diagram problem. I have a lot of different quantities, and they're kind of grouped together in different ways. So the way I'm going to do this is I'm going to make a big Venn diagram, okay? And I'm going to have 3 intersecting circles for the 3 options, right? I'll have a circle for leather, having leather. I'll have a circle for Wi-Fi, and then I'll have a circle for GPS. And I'll make sure that they all overlap like that. Okay, so when we fill this out, we're going to fill out starting from the inside out. So the first thing is, the most specific is this section in the middle here that has all 3. So it said that 60 cars have all 3, so we'll fill that in first. There are 60 cars. I'm using counts this time instead of probabilities. All right. Then if I go out to the next level, I can use this sentence here. It says 72 cars had leather and Wi-Fi but not GPS. So where would that be? They have to be in the leather circle and they have to be in the Wi-Fi circle, right? So that would be this, the leather circle and the Wi-Fi circle, right? But not GPS. So they're telling me that I'm not supposed to include the 60 cars here that had GPS. So they're specifically telling me that this number here is 72, right? Had leather and Wi-Fi but not GPS. Now, it's tricky depending on how this is written, right? The other way that this could have been written is, now the problem doesn't say this, but some problems will say something like this. They'll say there are 132 cars that have leather and Wi-Fi, and they won't say anything about the GPS. In that case, you have to take the 132 cars and subtract off the 60 you already know about to get that the rest of the cars the 72 that are left are in that remaining spot. But the way this problem is worded, they already kind of did that subtraction for us, right? Okay, so we have 60 and 72. All right, let's go on to another one. If I'm talking about this one, 70 cars had leather and GPS but not Wi-Fi, so that'd be in the leather circle and the GPS circle, right? This part right here, but not the Wi-Fi part. It just means this remaining open spot here. That's where the 70 cars would have to be, right there. Okay. I think actually, as I'm looking at this, there's something wrong. Yeah. You know, as I look at this problem, I think the total is actually incorrect. I'm going to have to make a change to the problem to make this work out. We'll continue, and then I'm going to make a change here. Sorry for that, but I'll make a change to fix it at the end. In fact, actually, you know what? I'm going to change the wording right now so that we can do this. Sorry, let me back up. And, uh, and now that I realize this as I'm recording this, that there's a mistake in the problem setup. So I'm going to change the problem slightly, and I apologize if you have to go back and redo the problem. So what I want us to do is let's cross off the but not GPS, and this part, let's cross off the but not Wi-Fi, because I'm realizing now that the problem is not formed correctly, and the but not leather. And I'll start the problem over again, and I think it'll make more sense why the numbers come out. The way it was formed, I don't think we could get a possible answer. So this is a solvable problem. Okay, so let's see. We've got our circle for leather. We've got our circle for Wi-Fi. We've got our circle for GPS. All right. So we know that the 60 cars have all three options. That's in the middle, right? But if I reevaluate this and say there are 72 cars that had leather and Wi-Fi, but I'm crossing out the part that says but not GPS, then that would be here. They have to be in the leather circle and the Wi-Fi part, right? But of the 72 cars, 60 have already been accounted for. So with that change to the problem, it means that that whole red football area has to add up to 72, but we've already accounted for 60. That leaves only 12 to go in there. This is actually more typically the way the problem is formulated. Okay, and then the second one said 70 cars had leather and GPS, right, which would be this football, leather and GPS, but we've already accounted for 60 of those 70, so there's only 10 left to go there, right? And then there's another one here that says that 75 cars have GPS and Wi-Fi, which would be this bubble, right? 75, but we've already accounted for the 60 in the middle, which leaves 15 out there. That's more typically the way the problem would be said. Okay, and then if I go back and look at these things, like 124 cars have leather seats, that means the entire contents of the leather circle has to add up to 124. So what you'd have to do is add up the existing 12, 60, and 10 that's in there, which would be 82, and subtract that from the 124. If you take 124 and you subtract out the 82 cars that we already have in there, right, that turns out to leave just 42 cars left, and that's what would go here. And you can use the same reasoning to fill out the GPS bubble, because it says that the GPS bubble has to add up to 118. So if you add the existing numbers 60, 10, and 15, subtract that from 118, you end up getting there 33 left there. And similarly, to handle this 99 number, that's what's in the Wi-Fi bubble here. We've already accounted for 60, 75, and 12 of that, leaving only 12 left. Okay? And then the way you find the number that goes out here is you add all the numbers up already inside the bubbles, and you subtract that from the total 186 cars that were sold. It turns out that only 2 cars did not have any of those options at all. So it takes a while to fill in the Venn diagram, but when you're done, you've done most of the problem, because now if I want to go back and find the probability that we have Wi-Fi, then I would just say out of the 186 cars, how many are anywhere in the Wi-Fi bubble. So then you can add up this 12, 15, 60, and 95 and 12, which is the 99. So 99 out of 186, which turns out to be 0.5323. Okay, and then if you want to do the second one, it's what's the probability that we have Wi-Fi and we do not have GPS or leather, and not GPS and also not leather, right? So the way I think of it is it has to be in, actually let me write that to the side so I can write this out. So when I see statements like that, and not leather, anytime something has to be true, it needs to be inside the Wi-Fi bubble. That means not GPS, means it has to be outside the GPS bubble and outside the leather bubble. Okay, so inside the Wi-Fi, but outside of the other bubbles would be this 12 right here, right? So it's going to be 12 out of the 186, or 0.0645. Okay, and then the last one says we want to find the probability that we have none of the options at all. And so we said there's only these two outside of everything out of the 186. And that turns out to be 0.0108. All right. So the Venn diagram is particularly good. It's good whenever you have combinations of options like this, especially if you can see there's overlap. If you have things like 60 cars have all three of these options, that's a good clue that you should use Venn diagrams. It's also pretty much required if you want to do subsection or subset kind of problems correctly. All right, that's the end of this video.